Okay, good afternoon, everyone. Thank you for registering for the Intro to UC's Advanced Research Computing Resources workshop. We hope you find it informative and useful. Please keep your cameras off and your audio muted, and this workshop is being recorded. I am Amy Latessa, a research associate with the Research Technologies Group in the Office of Research. And our team also runs and operates the Advanced Research Computing, also known as ARC facility, available to all UC faculty and students for their research and teaching needs. This workshop is part of the Data and Computational Science series. All workshops are free to the UC community, and we hope you will join us for other topics throughout the year. I'd like to welcome today's workshop host and guest speaker, George Turner, the Chief Systems Architect with Indiana University's Pervasive Technologies Institute. George has been working closely with the UC ARC team since 2018 to help us architect, acquire, and deploy UC's growing cyber infrastructure. UC's research computing capabilities wouldn't be where they are today without him, his knowledge, and his patience. There are also two students helping to facilitate the workshop, Faray Majid and Smit Patel. If you have trouble logging on or questions during the workshop, please type in the chat box and they will assist you, or they will get George's attention for questions. We will also have time for questions at the end. Don't hesitate to reach out to me or the ARC team with questions about the system or to discuss your work and data needs. We host monthly virtual consultation hours. You can make an appointment or just drop in. And without further ado, I'm going to hand the WebEx mic over to George Turner. And again, thank you for attending today's workshop.
Thank you, Amy. As one of my first physics professors once said, whenever you're preparing to do a live demo, preface it with nothing more predictive than watch this. So with that, let's see if I can share my PowerPoint. Well, as Amy said, I'm George Turner. I have my day job is working at Indiana University and what's equivalent to the ARC team there. We call it Research Technologies at Indiana University. I've been working in this high-performance computing field for about 20 years. I've been doing scientific computing for 40 years. My background is in astrophysics, and I've worked with many different types of data acquisition systems and compute systems, going all the way back to analog computing. So I can cover a wide breadth of questions. With that, the contact for anything concerning this talk should be arcinfo@uc.edu. And there's my address if you have any questions for me personally. Let's see. Can I make it go forward? Okay, first things first, this is an introductory tutorial. If you're interested in something more sophisticated, please let's start this conversation by sending an email to arcinfo@uc.edu. If it's just one or two people wanting a consultation, Amy already mentioned the monthly consultation times, and if there's enough interest, we're certainly willing to do another intermediate or advanced workshop. To log into the ARC, you must be either on campus or using the UC VPN. As Amy said, there are people standing by to help you if you have any trouble. And while you're trying to log in, I'm going to continue talking and cover some basic terms, the history of the ARC, and things of that nature. So to log into the ARC, you will need to SSH into your username at arc2.uc.edu, where username is your UC6+2. If you have any problems, like it says, I don't know what ARC2 is, there's the IP address. Again, if you have any problems, type in the chat window, and so there will be somebody there to help you. Some basic terms, the ARC with one C is the Advanced Research Computing Group. This is the team at UC that's working to establish the centralized research computing cyber infrastructure at the University of Cincinnati. If it's ARC with 2 C's, that's the clusters. We have the ARC1 and the ARC2, and I'll describe more of that later on. Storage within an HPC system, there's various different kinds. There's your home directories, where this is this is similar to your home directory on your laptop or your C drive, perhaps, if you're a Windows user. There's Workbench or Scratch Space. This is a storage device where you're supposed to put your data. It's designed for lots of people or lots of servers to be hitting it at the same time, doing parallel I/O. These are usually high performance, high bandwidth, and low latency file systems. In the future, we are looking to have some project space. This is where projects may store data that they acquire from instruments. It's meant more or less for longer term storage. It may not be as high as performance as the Workbench or Scratch Space. And then there's archive storage space, which is long-term deep storage. At IU, we use a tape-based system. So if you want to access a file that you stored a couple of months ago, it may take on the order of minutes for that file to be made available to you. As far as what we'll end up with at the University of Cincinnati, time will tell. There's also networks. We're all sort of familiar with the Ethernet that we use on our laptops or from our desktop servers to connect around the campus or around the world. That's the external connectivity. The ARC clusters have 10 gigabit per second uplinks. And then within the HPC systems themselves, there's what's called the switch fabric. And this is a high bandwidth, low latency networks. The ARC1 has an OmniPath fabric, and the newer ARC2, which we will be using today, has an InfiniBand. Both of these are 100 gigabits per second, and that's designed to share these Workbench storage. Workbench Scratch Space will be part of this fabric, and it will be able to have high bandwidth and low latency. You're going to hear me say these terms, high bandwidth and low latency, over and over again. And in research computing, these are the two entities that you're always dealing with. How fast can I move data? That's bandwidth. And what would it take me to move a 0 byte chunk of data? And that's your latency. Sometimes the latency is moving data from your memory to the CPU. Sometimes the latency is how long does it take me to move a file from storage into the CPU, and sometimes the latency is measured in how fast a human can type. So if this whets your appetite and you want to seek more information, there's I've given a list of some introductory tutorials. Shameless plug, we're going to be giving another tutorial next week on introductory Linux commands. So if you haven't signed up for that and you're interested, we have information on that. Slurm is going to be a big part of the topic today. Slurm is the resource manager that we use to schedule jobs onto the compute servers. So I've given 2 or 3 links here that I have found useful in the past. Likewise, you can do, the Google machine is very good at coughing up suggestions. And if you Google Slurm, there are lots of tutorials on YouTube. So. Slurm, I've already mentioned that, but it's essentially a cluster resource manager and a scheduler. Those are actually 2 separate things. A resource manager inventories the hardware that you have, like how many servers you have, how many GPUs you have, how much storage is available on these servers, how much RAM. The scheduler's job is to match up the jobs that the humans submit with the resources available. So you may request, I need one node with 2 cores and 3 gigabytes of RAM, and it's the scheduler's job to find that node out there that has the resources available to meet your demand, your needs. SSH is a command line interface. Hopefully you know what that is and you're currently already logged into the ARC cluster. One thing about HPC on clusters is it's very command line oriented. These type of computing dates back 20, 30 years. So while it's a lot of people today are used to using the pointy clicky methods of GUIs, a lot of work gets done on these HPC clusters via SSH. If you have Linux or Macs, there's an SSH client already installed. If you're a Windows user, PuTTY is a very popular SSH client for Windows, and that will allow you to connect. Throughout the slides, you will see where I put a hashtag in Linux. That's a comment. So anything after that hashtag will not be executed. So in some of the slides where we're doing commands, I will have a comment that needs to point out something. I've tried to make this to the point where you could all but cut and paste it. So if you accidentally cut and paste something with a hashtag, it will not get executed. STD in, STD out, and STD error in Linux or Unix parlance, that's the standard input, the standard output, and the standard error. So if you think of STD in as the input that you put when you type on your keyboard, or perhaps that's input from a file into your running program. STD out is what gets written to the terminal or an output file. And STD error is just a separate output stream where error messages can be written, say, to the terminal if you have a standard output going to a file. And path is very important in the Unix and Linux world. Path is a list of directories that's where executable applications are. And if that directory is in your path, you can just type in the name of the command and it will start running. Otherwise, you need to type in the entire path. There's not probably too many old DOS users around, but this would be a very familiar, all of these would be pretty familiar to old DOS users, but you know, we're going back 30 years or more there. Just a quick comment on the ARC and also about a lot of these slides. There's a lot of information that I'm just going to blow over. You can go back and review this later on. A little later on, I'm going to have you copy a directory over, and the latest version of these files the latest version of these slides are in that directory. So if you notice that there's a little bit of difference between the slides I'm talking from today and the ones that Amy sent this morning, you know, I do have a tendency of waiting to the last minute to get some things done. So anyways, on this slide, one of the changes is that we have Smit Patel and Faray Majad as members of the team. They've recently started working with us, and I believe Amy mentioned that they're standing by to answer questions, and if they're not able to answer the questions, they will get attention. So the ARC cluster, this is the pilot cluster. We started this back in, I believe it was December of 2018. We brought this cluster up and moved it into the data center. Then after the holidays, this cluster is currently active. We're not using it today because it's a lot easier to do these tutorials and workshops when nobody else is using the cluster. In other words, we're not interrupting work that people are doing. So if you want to get access to the ARC one, again, send an email to ARC.info, and they'll work with you on getting that done. It's an older cluster, well, old by compute terms. It's like 3 or 4 years old now, and that's late old age in computer. Usually, you keep these computers around for 3 to 5 years. We've been known to keep them at IU around for 7 years, but that's usually because we're struggling to find funding to replace it. 3 years, though, is usually the lifetime of an architecture. So when we build these clusters, you will hear us talking about we're going to keep this cluster for 3 to 5 years, and that's the basis for that, is that by that time, the new architectures will be coming out, and it'll be time to upgrade. That's not to say that what we have is not useful. When we first bought it, it was a hot rod, but again, 3 or 4 years down the road, there's a newer, flashier sports car on the market. Today we will be using the ARC2. This is the future of the ARC systems at UC. It was funded in part by the National Science Foundation Major Research and Instrumentation Grant with Dr. Prashant Kher as the project PI. There were additional resources provided by the UC Office of Research. This system has been architected for longevity and expandability. We will be adding to this cluster again over this 3 to 5 years. It's being designed to strategically integrate compute, networking, and storage into a cohesive environment. And again, this is the cluster that we'll be using today. The ARC1 pilot was more or less a means of, at UC to stand this up, and let's see what it takes to do this. What resources do we need, both human resources and data center resources and everything else that goes into running it. And then the ARC2, we're taking those lessons learned and we're doing this professionally. Excuse our dust, as I said, this is under construction. We currently have 19 nodes and 1 GPU node with 2 NVIDIA V100 GPUs. I leave it to you to look at these stats of what these are. If it means something to you, you'll be interested in it, and otherwise not. But in short, we have 32 cores per socket, 64 cores per server. Usually when you're submitting a job, you have some idea how many cores you need and how much RAM. There's 256 gigabytes of RAM in these. A common ratio tends to be 1 core per 2 gigabytes of RAM, maybe a little more, maybe a little less, depending upon what you need. And it also depends upon what you're computing. Biologists a lot of time only need 1 core, but they need a lot of memory. If you're rebuilding these sequences, you have a lot of sequences that you want to put in RAM, and you're sort of just knitting them together. If you're doing engineering type computing, then perhaps your models are able to take advantage of distributed memory type programming methods, and you need multiple nodes with multiple cores per node, and that's where you get into using the high bandwidth, low latency fabric. There's also a login node and a management node currently. You're currently, if you've been able to successfully log in, you're setting on the login node. And that's where you will compile and submit your jobs to run on the compute nodes on the backside. The login node is essentially just like a compute node that makes compiling programs and things easy. So when you compile it on the head node, it'll run on the compute nodes just fine. The funded expansion that we have, we will have about 1.5 petabytes of raw storage and 2 data transfer nodes coming in the first quarter of this year. A data transfer node is just a mechanism for moving data into and out of the cluster and storage devices. They're more or less just simple servers, just like the head node, but they're designed to not have humans on it. When you're doing all this data transfer, it sort of slows the machine down, and humans are rather intolerant of latency. So we keep this data transfer off on other nodes and leave the login nodes for the humans to do their work. Some additional compute and GPU resources are probably coming in the second quarter of the year. Part of the problem is depending upon the data center facilities there at UC. These systems take a lot of electricity and they put out a lot of heat. So the data center is having to upgrade both the power coming in and the cooling taking that heat out. And while we're not quite sure exactly what we're going to get, It should be about 50 compute nodes of the AMD Milans. Today we're using AMD Rome's, which is an earlier version, but it's the same generation of AMD processor. We'll have about a half a dozen GPU nodes, which depending upon what the pricing is on the time we purchase those, they could be NVIDIA V100s or A100s. So stay tuned. Okay, some basic Linux commands. Again, this is more or less meant for your review. I will point out a couple of these. Man is the help command for Unix and Linux. If you want to see how to use like the ls command, you do man ls and it'll give you more information than you ever wanted. A special version of this is man-k. And type in some keyword and it'll give you all of the man pages that have that keyword in them. So if you don't know what the command is you're looking for, say like copy, you can do a man-k space copy, hit return, and then you can sort through what it tells you. Excuse me. Most of these, again, are meant for your later review. Present. If you've never used a command line and you've only used a GUI, you're used to seeing folders, or we call those directories at the command line. So you move into folders or you move into directories, and these three commands: present working directory, ls, and change directory is related to that. CP, we're going to use that command as soon as we get to the tutorial here. Again, these are some commands that we're going to use during the tutorial today. If you want to look back or if you've looked these over, this is just what they are. And again, you can do like man space cat and again, get more information that you never want to know. So I will just mention editors. We're all probably used to the pointy-clicky GUI editors on our Macs or Windows machines. Again, we're working at the command line, so we got to create these files using a keyboard. Nano is a very easy one to use. VI is, any sysadmin will use VI because every Linux system will have it. You may or may not have Nano on a particular system. There's Emacs. We can get into editor religious wars about which editor is best. Emacs is very complicated, but it is also extremely very powerful. It's written in Lisp, and if you're a programmer and you want to program in Lisp, there's no limit to what you can do with Emacs. There are some GUI editors. If you have X11 set up properly, that means you have to have the X11 on your laptop. And when you do SSHN, it will automatically, most of the times, it will automatically set up the X connection for you. If it's not working, again, I would type in, send an email to ARC info and they'll help you get that through. But to see if X11 is working, do the command echo $display. If something comes back, you're set up and it should just work. If you just get a blank line back with no information on it, then it's not set up. And again, send a help email to ArcInfo and we'll get you going. Two GUI editors is gedit and nedit. If you're a programmer or if you're working with data, I would highly recommend that you check out nedit. I've been using this editor for 35 years, and it's still my favorite GUI editor. The nicest thing about it is you can cut and paste columns of data. I'll leave it there. Slurm, as I mentioned earlier, this is the tool this is the engine that will allow us to get work done on an HPC cluster. Not digging down too deep in these details. Slurm is the combined resource manager and schedule. If you're running on some systems, you about PBS or Tor, or maybe the Moab or Maui schedulers. With Slurm, these are all combined. Again, if you got a question, send it to ArcInfo and we'll answer it. This is more or less a rehash of what I mentioned earlier. The resource manager inventories what we have, what users are requesting, and the scheduler maps those. One of the cool things is that the scheduler predicts when your job will start. So we'll touch on that in just a little bit. A couple other things that's important on this slide is that our primary scheduler is the fair share scheduling, and I'll talk about that here in a couple more slides. We have what's called backfill. That means that the scheduler is trying to, for a big job trying to run, it's building up a reservoir of nodes. And if a small job can jump in there and run and get off before the big job can start, that's called backfill scheduling. So one of the things that you will put on when you're requesting resources is the amount of wall time that your job will need. And it's very important to get that number accurate. So when you're first starting off, you obviously won't know what that number is. So you might say, well, I need 24 hours if you think your job might run in 12 hours or 6 hours or whatever. And so you run a couple of jobs, and you find out, okay, well, you get some idea what the average runtime is. And so then it's, again, repeating myself, it's very important to have accurate wall times, because that allows the scheduler to more efficiently schedule not only your jobs, but everybody else's jobs. And it just makes things work much smoother. We do not have preemption turned on in this cluster. We have had it on the ARC 1. I don't know if it's still there or not. That's just where I have a bloody million jobs to run, and I just throw them into the queue, and so I can run on resources, but then when a more important job comes along, my job gets killed off because they can start over from the beginning. Usually these types of jobs only run for an hour or two, or not very long. So killing one off and restarting it is not. So if you ever hear of the open science grid, those are preemption type jobs. We also have advanced reservations. So if we were going to do this class on the ARC 1, we would have set up an advanced reservation for, say, 16 different nodes. And then whenever we started this class, we would have the resources reserved back for us. This can also come in handy if you're on deadline, or a reviewer says, well, we need you to rerun this to test this. And you got like 3 days to get it done. Send an email to ARC info, and more than likely we can work with you on that. So, this is, again, more, I touched on this mostly. FIFO is the old way of scheduling jobs. If you submitted 1,000 jobs, first in, first out, all 1,000 of those jobs would have to run before the next job run. This obviously irritated the users to no end. So this is where fair share was developed. The idea behind fair share is that we all have a certain pocketbook worth of what's called dispatch priority. So we all have, just keeping the numbers simple, we all have a dispatch priority of 100. And then the more I use the cluster, either more cores or run for a longer time, I use up my dispatch priority. So if it drops to, say, 50%, and somebody else has not used any of their fair share, their job will run before mine, except for backfill. As I mentioned earlier, those can jump in, run, and get back off. There's also an idea of expansion. And the idea behind this is that if I have a small job that's going to run for 10 minutes, I don't want it setting 3 days in the queue for 3 minutes of work. So these are sort of the fair share, the backfill, and the expansion. These are the parameters that we play with and manipulate to improve the efficiency of the scheduling. So this is just a quick example of the fair share scheduling. As I mentioned, the more you use, the more your fair share drops. When you quit using, it starts rebuilding over time. And eventually, if you don't use the system, you end up back with a full pocketbook of fair share of dispatch priority. So these are some Slurm commands. Sallocate and sbatch are very similar. Sallocate is to allocate the resources you need. As I've mentioned, you might need nodes, you might need cores, you might need memory. These are the three primary ones that we deal with. There could also be licenses or GPUs or storage or various different other things, but number of cores, number of nodes, and the amount of memory you need are the three big ones. So allocates those resources while you're setting them. You can think of this as interactively working with the system. Excuse me. Sbatch is for submitting. You have a script where you've typed in all your commands in, and you submit that file using sbatch to the queuing system. And this is where, the job might run in a few hours, or it might run in a few days. Or if you have 1,000 jobs you want to run, so you're doing a parameter sweep, well, there's more efficient ways than doing sbatching 1,000 files. Again, talk to ArcInfo and we can show you how to do this. But anyways, these scripts go into a queue and they sit there until the resources are available for them to run. srun, we will actually use this. Srun is the command you use to run a command on the allocated resources. Be it if those resources were allocated by sallocate or sbatch, srun runs on all of those allocated resources. SQ is very important for finding out how full is the queue, where are my jobs, what's going on. So SQ is the command you will be using quite a bit. This is more important for the batch stuff, things waiting to run in the batch queue. One of the most important ones is SQ-start. If you don't put -job ID, it will list all of the jobs that you can see, which is usually the whole system. So this gives you some idea of when your job will start. So before you write into ArcInfo and say, I've had a job in the queue for 3 days and why isn't it running? SQ-start-job ID will give you some idea. If it has if you're checking it over a period of minutes or hours and the start time is not really changing, then that's a pretty good indication that your job will start at that time. Also, this is why it is so important to get those wall times correct, because if you just submit a job and request 24 hours, but your job only runs for 15 minutes, then this is what Slurm is using to make a prediction when your job will start, when those resources will become available. If you notice that your job keeps getting pushed back, like, it's like now it was 1 hour and then now it's 2 hours a few minutes later, there's another command, sprio, which shows you how your priority is being calculated. As novice users, it's probably going to be rather difficult, but the more you use this command and the more you understand what's going on, this will become a very, both of those commands will become very powerful in understanding what's going on with the queues. Sinfo just gives you a state of the system. If you've submitted a job with sbatch, scancel is how you cancel that job. If you have a job running by sbatch, sattach is the way to attach to that running job, and sbroadcast is a way of copying files to all of the nodes that have been allocated to your job. Again, at some point, these commands will become more obvious as to how to use them. Okay, I have not seen any indications that people have had problems logging in. Now we're actually getting to the tutorial part of the workshop here. So let's type, let's see what our environment looks like. So the first thing I want you to do is do module. Excuse me, I can't type and think at the same time. So I'm doing these commands in another window at the same time. So if you do module avail, you get a list of the different packages that have been installed on the system. And at this point, we have Anaconda. So if you're a Python programmer or a lot of science domains create Python packages, and those are probably installed in Anaconda. There's a way to install Anaconda modules within your own home directory. So if we don't have the one that you need, get a hold of arcinfo at uc.edu and we'll work with you. Some things like ANSYS requires licenses. We restrict that access to those. So if you think that you have access, that you should have access to a certain program like ANSYS or MATLAB, something like that, and you're not able to access that, send an email to, I want to guess, arcinfo@uc.edu. The next command I want you to try is module spider. I don't know why they picked the names they did. So this is very much, the output of this command is very much like a module avail, but it goes into a lot more detail. The last time I did this tutorial, we only had one package on it, and that was the OpenMPI 4 one. And so it would actually tell you, this module spider command will tell you that if you want to load OpenMPI 4, these are the other packages you need to load at the same time. And hence, there's the next command. The module load GNU 9 and OpenMPI 4 will load the GNU compilers along with the OpenMPI software. So type that. And when you hit return, nothing changes. Module list. Now, if you do a module list, though, you will see everything that you have loaded. So we see the GNU 9, the OpenMPI 4. The OpenMPI also needs libfabrics and the UCX. These are mechanisms for setting up the communications that are required to utilize the switch fabric. So that's what we're seeing there. Now this tutorial, everything in this tutorial is in this directory opt/ohpc/training/fdw-hpc 210114. So if you do that cp-rp, that means do a recursive copy, maintain the permissions into the period is the directory you're setting it. So if you execute that command, it should just copy everything over, and you should just get back a prompt. If you get an error message, mention it in chat, and somebody will help you with it. The next command is this change directory into the. Oops, how did that happen? Fat finger strike again. Yes, okay, sorry about that. So CD into that FDW, that's the Faculty Development Workshop, HPC, and today's date, and do an ls-al. And what you should see is at the top, you'll see a dot and a dot dot. Again, remember dot was the current working directory. Dot dot is the directory above. So we executed the copy command in the directory above, and we copied that whole directory and everything into it to here. So, and we have now moved into this directory or into this folder, and these are the files that were in that directory that you copied. The first thing you'll see is the AAA readme.txt. If you do the, let me see if I have, no, just the copy. If you do cat on that AA, just type two A's and hit the tab key. This is what's called tab completion. Unix programmers have a tendency to be lazy, and so learning this tab completion can make your life a lot more enjoyable. So if you do cat space AAA readme, what you will see is all the commands in this tutorial. Everything that's on the slides is in this this file. So you should be able to literally cut and paste from this file and not have to worry about typing in these things. With that said, okay, moving on. We got to be in the right window. So now let's take a look at a simple program. In the world of Unix, Hello World seems to be one of the simplest world C programs, and it's always used as an example. So if we do less HEL tab key -C, your screen will show the simple Hello World.C program that we're going to compile. I'm not going to go into too much on this. If you want to stop by a workshop, or I mean one of the monthly consultation, more than happy to go over and describe what's going on here. We'll probably have to do actually, Amy, if you contact Amy via arcinfo@uc.edu, she schedules classes with Exceed classes, and they go into this MPI type programming. But just quickly looking at it, there's an initialization. The COM rank and the COM size determines how big of the resources that have been allocated to you. The print says hello world, I am what of what, and then we do a shutdown. So what this program is going to do is run on all the resources that we have allocated.
Hey, George.
Yes, ma'am.
Could you share your interactive screen?
Is it better?
Yes.
Is it good enough?
I think so. The users should probably comment on that, the attendees.
Because I can't see it.
Yeah, I think the screen is much better now.
Yeah, I think it's better.
Okay. Good.
All right, thank you. Pardon the interruption.
Yep. Like I said at the beginning, say nothing more predictive than we watch this. So moving on, we did a. I'm going to do this less hello.c again, and what I did there, I just hit the up arrow. So again, people are lazy. So here's the program I was talking about. What you will see is, if you're not a C programmer, it's probably just a bunch of mumbo jumbo. But there in the middle part, we see an MPI initialize, MPI COM rank and COM size. So that's just getting, like I said, how big of a program am I running? And then we print it out to the world. And the original Kerningham and Ritchie C programming book from the 70s, they just said, the whole idea was to prove that this program had run would print hello world out to the outside world. And then the MPI finalized, closes the, shuts everything down. So, next thing we're going to do is we're going to compile this program. So what this is doing is we're going to use the MPI CC compiler. And MPI is message passing interface. So the way you use these giant clusters is with a bunch of servers in them that you pass messages back and forth. And so that's why we're using a message passing compiler. The -O is for the output file. I want it to be called hello, and the input file is hello.c. So I hit return, and if I do an ls, we now see this hello if I highlight, can you see that?
Yes, we can.
Okay, cool. That makes life a lot easier. So compile command up here created this output executable from the hello.c program. Now the next step is we want to use Slurm to allocate some resources. So we're going to use the sallocate. Now remember, I could use sbatch as well, and we actually cover that at the end of the workshop if we have enough time. So I want to allocate 2 tasks. So I hit return, and the scheduler is going out there trying to find what I have asked for, and it has found it, and it says that I'm ready to run. So we use the Mpi cc command to compile. We're going to use the Mpi Run command to run that program we just compiled. So what it's saying was is we started up 2 programs. I asked for two tasks. It numbers in programming. You always start from 0 or you start from 1. So I started up 2 tasks, task 0 and task 1. And each one of those printed out to the terminal. And that's the output that I'm seeing. Okay. Now let's try a slightly more sophisticated example. So the next thing we're going to do is we're going to look at a program called connectivity.c. As you can see, there's a lot more information here. Now I'm going to hit the space bar so I can jump down. So this is the bottom of the file. I can use an up arrow to move up. I can move a down arrow to move down. I'm not really going to go through this in detail, but essentially what it's doing is again, we're going to come up, the program's going to get a hold of the resources that it has. The program will start up on those resources, and then it's going to do some checking connectivity, say from task 0 to task 1, and task 0 to task 2, and task 2 to task 1. So it's going to check this connectivity back and forth between all these running programs that I have going out there. So now I'm going to type the Q command for quit. We've got to compile it. Again, we'll use the Mpi cc compiler. Hit return. Let's see. Oh, there's a command that I put in the slides that I did not do from the hello world command. I did not exit. I'm going to exit now. Okay. So what that did was all those resources I had, it got rid of them. So what I'm going to do now is essentially go back and get those resources again. So I get back online with the tutorial. For sallocate, give me 2 tasks. Says I'm ready to go. One thing to notice, up here it the first time I did this, it said job granted allocation 66. This time when I did it, oops, sorry about that. Job allocation 69. So what this tells me is that only 2 people there were only 2 other jobs from the time I did the first command to the second command. So if you're having a problem, type into the chat. Or if I'm going too fast, because I know all the tricks, so I can blow through this. And if you're sitting there trying to type this all in, you can imagine that it could be frustrating. Anyways, so I've allocated two number of tasks is essentially the number of cores. So I've allocated 2 cores for what I want to run. Now I'm going to do the Mpi Run Connectivity command. So type it in, hit return. So two tasks were able to talk to each other. Okay, not very exciting, not very interesting. Let's exit. Moving on to the next one. Now instead of tasks or cores, we're going to allocate nodes. So a node is a physical server. A physical server, that's just like your server at home or your laptop. Within that server are sockets, and each socket has a CPU, and that CPU has a number of cores. I think I mentioned earlier that these have 2 sockets, and there are 32 cores in each socket. So we have 64 cores, where we can run 64 tasks on one node. Now we're going to ask for 2 nodes. Rather than running on the same server, they're going to be running across the two nodes, across the 2 servers, and they're going to use this high bandwidth, low latency switch fabric I've mentioned a couple of times. So allocate them. Goes out there and looks for them. And now we're ready to run. Okay. Now we're going to run Mpi Run Connectivity. So hit return. And again, not much output comes out, but it did successfully run on 2 processes. So just because we know what we requested to allocate, we now know that we can talk between nodes, which is a little more sophisticated than talking within the memory. Okay. We type exit because we want to get rid of that allocation. Now we're going to get a little more sophisticated. This time we're going to run 2 tasks on 2 different nodes. So that's allocate. -- nodes equals 2, and I want 2 cores per node. You can think of the term task as synonymous with process. So if you hear somebody talking about a process, that's a running program on the system. So we're going to have 2 processes running on 2 cores on 2 different nodes. So we're going to have 4 processes running. So we do our Mpi Run. Actually, let me show you. Again, I've been cutting and pasting. It's very easy for me, but I can do this tab completion with commands as well as looking for files. So do Mpi. I hit tab once. I don't know if you heard that beep. It's saying that there's more information. If I hit tab a second time, it shows me all the Mpi commands. Okay, so I can do Mpi R and hit tab again, and it'll auto-complete. I typed in CON, hit tab, and so then it expanded out to connectivity. And then I don't know if you're hearing that beep again, but that it means that there's more options. So if I hit tab again twice, it will show me all of the possible things I want to do. Well, I don't want to run the connectivity program, so I have the information right now. So I hit return. Now we get a lot more information than we did out of a simple program when we were just running 2 nodes with 2 tasks. Now we can actually see, since we had 4 tasks out there, we had more than just one process talking to one other process. Now we're showing that we have all 4 of these tasks running and how they're all able to talk back and forth. So when you're running these very big sophisticated programs, or like after a maintenance, these are the types of programs a sysadmin might run to make sure that they can get everything talking back and forth. So this is very simple. It just gets it up, checks your connections, and then shuts it back down. So now I want to exit again. So the next example is 2 nodes and 4 tasks per node. So let's see. Oh, I'm cheating again. So what I'm doing is hitting the up arrow, because I know I've already typed this command once before. I don't want to type it in. So I just hit the up arrow and find the command and hit return. That way I don't have to cut and paste, or I don't have to type it in. If you're fat-fingered like I am, I mistype everything. So when you learn these little tricks, it's very helpful. It keeps the frustration level down. Once I got it typed in once, I don't have to type it in. But anyways, without going through all the output there, if you want to take the time and a pencil and a piece of paper, you can actually see that everybody talked to everybody, and there was no problem. So 2 nodes and 4 tasks, so everybody's talking back and forth to everything. Let's type exit to get out of our Allocate. A little bit different one now is that we're going to do 2 nodes with 2 tasks per node. So here we end up with 4 processes that'll be run. Let me show you another little trick here. Since I know I typed Mpi Run before, I can do an exclamation point, Mpi, and it will run the last program, the last command, that had Mpi in it. So I typed in exclamation Mpi and I hit return. And notice that it went back in my history and it found the last command again that said Mpi. And so it filled in run connectivity. Anyways, I don't know if I had pointed this out before. Compute 1 and Compute 2 are the host names. Rank is the rank, you'll have like a rank 1, or rank 0 on Compute 1. You'll have a rank 0 on Compute 2, it should be. Okay, I need to look at it here. So anyways, that's it. And for some reason, I have just typed Mpi. We have no allocation. If I type run Mpi Run Connectivity, what it did was it ran on every core on the current machine. So if you add those all up, there should be 32 processes. So, and they're all able to talk amongst themselves. A little bit more information on this talking back and forth. When they're all running on the same node, they're actually using RAM to pass these packages or these messages back and forth. And what I stated earlier, when you're running on different nodes, they're passing these messages over the switch fabric. So it's very much faster to pass these messages through the RAM than it is over the switch fabric. And the reason they're faster is the latency is the primary reason. I mentioned latency and bandwidth. They're always battling those two issues. So the latency of passing a message through memory is much lower than passing it across the switch fabric. So is there any questions now with the simple, what you can do is once, you can play with these at your own pace and sort of see more what's going on. As long as there's no questions, I'll move on here. The big difference is now that instead of using srun, or I'm sorry, sallocate, this is the interactive sort of way of doing things. We're actually going to use a batch script and submit it using sbatch. So usually, this is the way, once you get your programs all debugged and you're just running them, running your models or something like this, you'll be using the sbatch versus the srun. One of the, taking a quick tangent here, these HPC systems are usually, a lot of the work that they do is running models. And the biggest model that affects most people's life is the weather model. If you're like me, I check the weather 2 or 3 times a day, and have the models changed? You know, is the rain going to get here at 3 p.m.? Is it going to get here at 6 p.m.? So what's going on with these giant models is, and digging into the MPI a little bit more, is that you cut up the problem. So you did what we call domain decomposition. So you take, just to keep the math simple, let's say we have 50 nodes, and they only have 1 core per node. And one server is going to calculate the weather model in Illinois. The next server is going to calculate the weather in Indiana. And the next one's going to calculate it in Ohio. So they're able to calculate just using Newton's equations of motion that we learned in the 5th grade. I don't remember. But integrating Newton's equations, you calculate mass and forces and acceleration and how are things moving, and you pump energy in, and that causes things to move. So at some point, though, you're going to have the wind blowing from west to east. And so the model that's running on Illinois needs to pass off to Indiana. Like, well, here I'm sending this much mass of air to you that has this much energy. It's this temperature, it's moving this fast, so it has that much momentum. And so it passes a message from one server to the next. And the same thing going from Indiana to Ohio. So at these boundary conditions, you're passing messages back and forth. You're able to integrate, you're able to calculate everything within your domain, but at the boundary conditions, you have to use these messages to pass back and forth. And again, going back to the bandwidth and latency issue, a message has a size, that's a bandwidth issue, and the time it takes to send that message to the next server is a latency issue. So, okay, so back to where I took off on that tangent is that we're going to use the batch queuing system now rather than using these things interactively. So we're going to take a look now at the let me do. So now we have, we're going to look at this hello slurm file. This is the batch file that we will submit using sbatch to the slurm system, and it will run it at some point in time. Taking a look at that, hello tab.s slurm. So again, I just did that type s or .s and hit tab again, hit return. So this one we actually have to go through a little bit more than I did with the C program. So for scripts on a Unix or Linux system, the very first line you see this hashtag exclamation. And the next thing is what's called a shell. So we're using the bash shell. And another thing about the Unix and or Linux, I use those terms interchangeably. Unix is trademarked, so technically I shouldn't be saying Unix, I should be saying Linux. But so anyways, the first 2 characters of a file on a Unix system mean something, okay? So if you have a device driver out there, or you have a database, or you have an executable, or whatever it is, the first 2 bytes of that file mean something. And this hashtag exclamation point means that whatever follows this is the program you need to run to interpret what's in the rest of the file. So you'll see this all the time. It's something to we'll probably cover a little bit more in the introductory class next week if you're interested. I mentioned earlier about when you using these scheduling and resource management systems, what you're doing is you're requesting resources for a length of time. So here I'm asking for 600 seconds. This number is in seconds, so that would be 10 minutes. We use the nodes and the number of tasks per nodes earlier in our Allocate. So it means the same thing here inside this file as it did when we typed it in on the command line. A couple other things to notice is that the very first character is the comment character. So if I was just to run this script on at the command line, we'll go into this next week, these lines would be comments and they would not be interpreted. However, this S batch does mean something to Slurm. So when we submit this command to the Slurm resource manager, it will take and act on these commands. And here on the fourth line, you'll see that I actually, instead of just doing hashtag SBatch, I did this, I made it just different so that the second character wasn't an S, and so the Slurm job manager will not interpret this command. So a lot of people, when they're running jobs, say you got a job that's going to run for 3 days, you want to know when it actually begins, because you may have been sitting in the queue for a little while, and you want to know when it ends. So this is how to get it to send you an email when the job begins and when it ends. If you do a man on SBatch, it'll also tell you some other things that you can get mailed about aborts. I think there's one or two other things. But the beginning and end are the ornament. Again, these are comments. Notice there's no SBatch as the second character. So these really are comments. I pointed out earlier when we were doing the Allocate, I could tell how many jobs. It said like job ID 69, job ID 72. When we do the SBatch, it will create a output file that's called slurm-nn.out. So if my job was 62, that NN would be 62, slurm-62.out. Well, if you're running, okay, I'm an astronomer. I might be doing calculations on accretion disks, and I might be doing calculations on pressures within suns or something. This slurm NN in my root directory doesn't mean anything to me. So I can change that name of that output file that slurms by using this syntax here. So I can either do it on the command line, I could type all of this on the command line, or I could create an SBatch line like I did up here and put this on. Okay. This is just saying dash out. You can do man on SBatch and it'll explain all this. But essentially, I want the output file to be named the name of the input file with .o. So see that .o there? That's the .o here. This dash J is %J is the job number, and then the date. And this funny syntax here is just saying year, month, day, hours, minutes, seconds. So that's how I get this. 2020, October 22nd, 8 o'clock in the evening on this Monday. So you can tell when I actually did this exam. Moving on. At the beginning of the workshop, we loaded some modules. This is not strictly necessary inside the batch script. If you've already loaded these modules at the command line before you do the SBatch command, this will be in your environment. Let me actually show you something here. Print env. So I'm going to print the environment. Okay. So you'll see all of these things before the equal sign. And these are different environment variables. I think I had mentioned path somewhere before. So if I do echo dollar, let's just take log name. I do echo log name. That's an environment name. My login name that's my UC6+2. Okay. So anyways, going back to the hello Slurm, if I had loaded, if I had loaded the modules again at the command line and then submit the SBatch, Slurm takes all those environment variables and it keeps them and it runs the job with those environment variables. But let's say I wrote this script a long time ago and I just want to submit it and run. I can put this inside the batch script to make sure that those modules that are needed will actually get loaded. This is just telling me, in the output file, will tell me what data was run. Excuse me. We're printing some variables to the output so that I know, like the job ID, how many nodes, how many tasks per node, and node list is actually which compute nodes it was running on. This is just another way of getting the same information. I run a command. srun is a way to run. srun is very much like the Mpi Run command I was using earlier. So you can almost think of them as synonymous. srun will run a program on all the allocated hosts. And all I'm doing is, if you actually type bin hostname, it'll tell you the hostname of the one. Oops, I see a typo. I did not fix this for this class. Now you get to see how you edit something. Apologies. So now I'm just going to CD into the directory where this stuff really is. Notice again, I'm going to use the Mpi Run. Hello. This syntax is the first time I've showed this. Remember, period is your current working directory. So I could have many different hellos in my path. If you'll remember when I said that earlier, that says run this one in the current working directory and ignore all those other hellos in my path. Whenever a program runs in Unix, this variable is the exit status. So what I'm doing is taking the exit status from when hello ran and sticking it in this environment variable. Success is 0. Anything other than 0 is a failure. And then I'm printing that to the output file, and I print the date that I exited. And that's the end of the program. Should be. Yep. If you use the VI editor, I did colon, and it popped up a prompt, and I'm saying right click. So back to the slide. So we did the hello Slurm. Now I'm going to use the SBatch command. I'm telling Slurm that I want 2 nodes and I want 2 tasks per node. Now, if you remember back, I had within that script, or within the hello.slurm file, I had told it how many resources I wanted. The resource request on the command line overrides whatever is in that file. Okay, it's sort of, say I want to run it to do little tests here, but when I go into production, I want to run it across, say, 20 nodes and use all the cores, then I'm going to change that. Anyways, now I have submitted this job to the queue. breaking from the, so, okay, it already ran. I'm not surprised. So remember earlier I said that the output file would be named slurm dash whatever my job ID number was .out. So here it is. It Slurm went out there, got the resources, ran the job, and wrote the output. So I do less slurm. I did less slurm SL tab, and since that's the only slurm file name, it knew to complete all the way out. So, and it did just what I showed in that batch script. This is the date time we started. These are the environment variables. Job ID 83, we saw that outside the file. I wanted 2 nodes and I wanted 2 tasks per node. And it gave me 2 nodes. Compute is the first name, compute 1 and compute 2. So if this had been 1-4, I would have been running on 4 different nodes. Compute 1, compute 2, compute 3, and compute 4. So this is part of the lingo of Unix and Linux. I'm getting to understand this type of nomenclature. Here, if you remember back to the script, I had it run the command bin host name, where all that command does is print out the name of the host. So you will see I have 2 compute 1s, I have 2 compute 2s, and this number is the task. So again, starting from 0, I have 4. And this is the line within that C program where it printed out, it said, hello world, I'm 0, 4, 1, 2, 3. When you run these in the real world, if you have a big program, they won't always come out 0, 1, 2, 3. They will be in different order, so don't expect that to happen. Again, the exit status is 0, so I know that it ran all the way to completion, and there was no problem, and this job was done at this time. I'm in less, so I'm going to exit out of less by hitting the Q key. I didn't see. Yes, okay. Slurm. I didn't see Slurm, but tab .slurm. So looking at the Slurm back-to file for connectivity, it's very much the same. Of course, I know that I know the CD directory is going to be on. Insert. Copy. Paste. Escape. We have an insert node. Colon. Right click. Make sure I didn't mess anything up. Okay. Yes. Oh, here's another place. So on the last command line, the last parameter was the name of the file. So I can use the last parameter on the last command by doing this exclamation $. Okay. So let me give a shortcut. If it's simple, you might not need to do much. So I have put these various different things and commented them out, these commands to the Slurm Resource Manager. I take these and play around with them. These are essentially the same things that we did when we were doing the S allocate mechanism above, 2 nodes with 2 tasks, 2 nodes with 4 tasks, 2 nodes with 2 tasks per node, run them, look at the output, see what the difference is,
and see if you can figure out what's going on. Obviously, if you don't understand it, send an email to arcinfo. You see that? Most of the rest of this is the same. I would suggest you play around with this and get to know how you can change the output name. Start time, what are those environment variables? Tell me what mode you were running on. Change directory to where this program is. This is the part that I screwed up. So if you're doing the cut and paste method to follow this, this is where it's going to fail. Another thing, this tilde, you may have seen it once or twice. This tilde means home directory. Okay, so when we copied all those files over from the system, we were setting in our home directory. We said copy recursively everything in that directory. And that's how it ended up off of our home directory with that same name. So what I'm doing with this command is I'm saying change directory into this directory that's off of my home directory. In other words, where all of these programs are. Mpi Run. I could use srun here. The reason that I used Mpi Run is that when I did this demo the last time for data days, there was a bug in the srun command. So I can use these interchangeably. Exit status, I hope it's 0. I print that to the output on the time that I quit. I'm going to hit Q to get out of that. S batch, cut, paste this. So again, 2 nodes, 2 tasks per node. So I'm going to be running 4 tasks on 2 different nodes. And I'm going to return. Oops. Notice that I didn't cut and paste the S for S batch. Job 84. Job 84 is completed. And notice that time when I hit tab, there's an 83 and an 84, so it got to the 8 and it says, well, you need to tell me which file it is. So I'm going to type 4 and we'll finish it out. And as we saw with the S allocate, this is the output that we made from that. If I'm not mistaken, that's the end of the tutorial. Are there any questions? Or is there any discussion you would like to have? Now would be a good time to, if there were other things you wanted to see. Excuse me, I muted myself. Trying to do that. Sure. Somebody tell me how to get out of share mode.
Is there a toolbar for you at the top of your screen, George?
It says you are share. Oh, stop sharing. There you go.
Mm-hmm.
Yay. Okay.
Okay. We do have a question here in the chat. I may have missed this, but how does a person transfer data out of the system once a run is complete?
There's an SCP command. Actually, I'm going to write these questions down so that I know to include it in the tutorial going forward. So let's see if I can actually show how I would do that. Share. So are you seeing my screen again?
Yep.
Okay, remember the man command? That's the help command. There's a command called SCP, which is secure copy. If you'll remember back when, well, about halfway through the works, when we first started the actual hands-on tutorial, we did a CP. Okay, that's copy. Well, SCP is the secure copy. So this is how you copy something from one node to another node. And if you'll remember, we used SSH to log into the system. This is the SCP. So SSH means secure shell. SH is shell. SCP is secure copy. So I'm going to look at the man page for, oh, no man. We'll have to take care of that. But anyways, I would say, looking at what files I have here, say I wanted to copy this to my IU account, I would say like slurm 83.out to karst. Actually, cool. So what this is saying is that I'm going to secure copy this file that's in my current working directory to a host name. Everything before this colon is this is my workstation on the IU campus. And I want it to copy it there with my current username. So if I actually try to do this, this will fail because my UC 6+2 is not the same as my IU username. So my IU username is G at. So that's how I change the name on the foreign host. So if I were to do this, I don't know what firewalls are in place. Anyways, what it should do is it should come up and ask me for a password, my IU password. There are also SSH keys. So you can, these are, if you know what PKI or public key, public key infrastructure. So this PKI is where you have a public key and a private key, and the private key is like a password, and the public key is on the other side, and it validates the handshake, and it would automatically do the copy. So this command is failing. There's a firewall somewhere that's not allowing this to occur. Which did that answer the question? And likewise, the other way, if I was like sitting on my laptop, actually, let's see, you probably can't see that. When I copied over the files, like the this file, this is the PDF of the slides that I was presenting. I mean, I was working down on that on my laptop, and how I copied them from my laptop to there was more or less reversing. It would look something like SCP, UC tab to arc to dot UCW colon. And that's enough to get it there and copied into my home directory. Now, if I wanted it in a subdirectory, I could do like the tilde, which means my home directory, dot temp slash dot whatever. So those directories would have to pre-exist before I could copy them into them. But so that's how I copy something from my laptop onto the ARC2 system. Down the road, we'll have data transfer nodes. I mentioned those earlier. You'll use more sophisticated commands like globus or there's a one that biologists and medical type folks use from IBM. It's a very popular one. But if you're copying big files, you want to do that through the data transfer nodes, like I mentioned before. We'll have some knowledge base articles on how to do that once we get that up there. Did that answer the question?
Yes, he said it did.
Any other questions? If you have any suggestions for information that you would like included in this, again, send that info to arcinfo.uc.edu. Feedback is very welcome. When you have an expert teaching something, that's probably the worst person to have teaching the class because they know everything. So it's actually sometimes more useful to have somebody that doesn't know everything teaching it, because they'll actually put it in a form that is more digestible. If there are no questions, I'm done. So, Amy?
Okay. Yeah, if no one else has questions, I'm gonna put the links to more info on ARC, how to request an account, because this account was set up for you just for this workshop. Our email info that George has mentioned several times so that you can get in touch with us or set up a consultation, because we know a lot of this there's a lot of learning curves and everyone's at a different level. So don't be shy. Come talk with us. We want to help you. We have a small but capable team. And then also a link for, again, the Data and Computational Science series, which is updated. There's a bunch of different workshops some are a little bit more advanced research computing heavy, some are data management, visualization. So there's a whole plethora that are there to help you get your research and education. And we also take suggestions. So if there's something you'd like to see, don't hesitate to email me. So I'm going to leave it there. We'll end a little early. Everyone can enjoy the rest of their afternoon. I hope that this was informative. We will, we've shared the slides, but because this is recorded, this will also be available and posted on probably the DCSS website, but I'll let you guys know with a post-workshop feedback questionnaire. So thank you all for attending, and get in touch with any questions. Good luck with your work. Thank you.